Okay, page 84, number 31. I don't have an air hockey table or anything to do this experiment, but it just basically tells you to do the puck against the wall and see what angle it would do. If it's at a 45-degree angle, it would go at the 45 degrees, so you can predict where it goes. And number 32, in a pool table, note that no matter how complicated the collision of the balls, the momentum along the line of action of the cue ball before the impact is the same as the combined momentum, and its conservation more clearly when rotational English is not impacted to the cue ball. When English is impacted by striking the cue ball of off-center, rotational momentum, which is also conserved, somewhat complicates the analysis. But regardless of how the cue ball is struck, in the absence of external forces, both linear and rotational motion are always conserved. Both pool and billiards offer a first rotational exhibition of momentum of conservation in action. In this experiment, it says to pour some dry sand into a tin can with a cover. Compare and shake the can for a couple of minutes. Predict what occurs. What your explanation? Okay, so this is sand that's just dry, that has regular temperature, and this is the sand that's in the tin can. I'm gonna shake it for about 5 minutes and then see what happens with it. The average degree change with this experiment is 1 to 2 degrees higher than normal. How does this work? The shaking of the sand is a form of kinetic energy. The friction of the sand running against the sides of the can and the sand itself produces kinetic energy that turns into heat energy. Some kinetic energy is converted into energy known as sound waves, which you can hear when you shake the can. So do this for about 3 more minutes and then dump it out and see if it changed any. I don't really have a thermometer or anything to check the temperature, so we're just gonna do it by feel. And this sand's pretty room temperature, kind of cool. It's just regular play sand. I don't know if side to side or up or down matters. It's been about 3 minutes. I'm gonna wait till 1 more minute and then we'll just dump it out. Yeah, it's definitely a little bit warmer. Not too much, because it's only like 2 to 3, maybe 4 degrees higher, but you can definitely tell a distinguishable difference. Cordell,
Ow!
it's not that hot. But it does warm it up a little bit more than the regular sand would. The next experiment is to place a small rubber ball on top of a basketball and drop them together. If the vertical alignment remains as if they are falling to the floor, you'll see the small ball bounces usually higher. And the question is, can you reconcile this energy with conservation? So, drop it. The little ball does bounce higher, and the reason for that is when the balls are dropped together, most of the momentum from both balls, so you have momentum on both balls, as they're dropped, the energy is transferred into the smaller ball. If the smaller ball receives all the kinetic energy from the momentum bouncing off the floor to the large ball, it will move all the energy from the larger ball into the smaller ball, pushing it higher. Energy conservation, the definition is principle by which the total energy remains constant in a system that is not subjected to external influence. This procedure is not continuous or has a constant system of energy, so I would say no, it does not reconcile with energy conservation. And this is the second lab on page 114 and 115. This is the illusion. There was an illusion that was on there, but this is my own illusion. Although observers may perceive on illusionary direction of motion, the moving contour always appears rigid. If a pencil is held loosely off the center and wiggled up and down, it can appear to undergo a non-rigid bending motion, although the pencil remains physically straight at all times. So what you would do is just barely press your fingers on the end and then slowly just loosely wiggle it up and down. I don't know if the camera will capture it, but it's supposed to be an illusion to where the pencil looks like it's actually just wiggling, but it's actually not, it's just straight. I don't know why it does this with your eyes, but it's just an illusion. This is the dangling beads. I had to make my own little contraption with a ruler, string, and beads, and they're 1 centimeter, 4 centimeters, 16 or 9 centimeter, 16 and 25 centimeters, and it's supposed to show trajectory. So if I turn it up, hold the stick horizontally, you will have the version of figure 4.16. Hold it at a slightly upward angle to show version of figure 4.17 left, and hold it downward to show figure 4.17 right. This is a projectile motion, is a form of motion where all objects move symmetrically, called a parabola path. The path that the object follows is called a trajectory. Projectile motion only happens when the force is applied beginning the trajectory of the object. So this would kind of show the trajectory of the projectile motion. And then with friends, whirl a bucket. We don't have a bucket, but I have this cup of water in a vertical upside down, spin fast enough for the water not to fall out. The water in the cup is falling, but with less speed than you give the cup. Tell your friends how your cup swinging is linked to satellite motion. The satellites in orbit conventionally fall towards the Earth, but not with enough vertical speed to get closer to the curved Earth below. Okay, so what it's saying is that as you spin the water is gonna go to the sides of the cup, and this is gonna keep it from being on the bottom of the cup. So in theory, if you turn this cup upside down, if you do it fast enough, the water will stay spinning on the sides of the cup. But I've tried this experiment a couple times off camera, and it hasn't worked because I think the bucket has a larger area for the water to circle, and I think the smaller the area of the water circling gives it less time to fall. So it would fall quicker with a smaller cylindrical shape than a larger. So I don't think this will work when I spin it upside down because it's just been making a mess all over the floor. But the satellite motion is basically the satellite's orbiting the Earth, and gravity's not pulling it down. So basically this will be like the satellite moving around the Earth, and the middle would be gravity pulling it down, but it wouldn't pull it down if it was in a larger bucket. But unfortunately, with this experiment, I couldn't get this to work. And that is all. Thank you.